evening. We are separating between you and the end of the day. I'm sure everyone is waiting for dinner, so we'll try to entertain you so you all kind of have a good time. So we're excited to present to you today how Anthropic uses GKE and TPUs to scale resilient AI. So first presenting, so I am from GKE Engineering. With me, Kavitha from GKE Product, and Artur from Anthropic will present together. So the goal of the talk today is to discuss about dynamic slicing. Dynamic slicing enables you to run more efficient workloads on your TPU capacity and help you manage your capacity. So Google has been in the business of TPU now since 2015. As you all know, different generations of TPU. Yesterday, Sundar and Thomas Kurian presented the TPU V8. So we're very excited to see TPU V8 coming into place. As you all know, basically 2 out of the 3 biggest models in the world, or the most advanced models in the world, were trained on TPU. So we're very proud about this fact. We basically are going to we launched 2 different TPU versions. One is zebrafish for training, and sunfish for inference, and RL. So we have training, inference, RL with those new models. Those kind of models are, chips are state of the art, 4 times better data center networking, 2.7 times better price performance, 2 times better price per watt, and we all know that currently getting a watt is quite hard. In terms of GKE, so here in kind of a small room, I can tell you basically almost all of cloud TPU is run through GKE because of all the values that GKE provide as part of the training and inference workloads. In terms of what GKE provide, in Google, if you think about in Google, we try to optimize in all the different layer of the stack. So if it's helping with obtainability, how do you get your capacity in the right place, around co-innovation with all the different layers, with dynamic slicing, cluster director, resiliency, automatic failure recovery. Around the training, actually, we announced a few hours ago, we announced that GKE currently support 250,000 nodes in a single cluster, 1 million chips, basically. It's like far beyond anyone else in the industry. We basically, in terms of inference, so we developed a GKE inference gateway, which give much better, lower, 30% better serving time, 40% higher throughput. All kinds of those are really important properties to get efficient inference. And we integrate with LLMD. Actually, we developed most of LLMD, integrate with LLMD, with Ray, give you all as customer a lot of capabilities across getting utilized for your TPU capacity. With that, I will transition to Kavitha to show our latest innovation.
Thank you, Iftach. That's amazing. I think GKE has so much of AI innovation, both for training and inferencing, and I think that was a great presentation, Iftach. However, I do know I'm the one between you and then the concert and then the happy hour. I'm sorry. However, I'm going to make it worthwhile for you. I'll try at least. We're going to make it more interactive, so let me see who dozes off. I'm just going to call on the people who's dozing off, and you're going to answer the questions. I am very, very, very excited to show the next set of innovations that we are bringing on TPU. Before that, let's look at what is there today. Historically, GKE TPU configuration is extremely node pool centric. What does that mean? That means that your topology of your TPU configurations has to match exactly your node pool configuration to land your workload. Let's take an example here. Oops. I have to use mouse here and then play for it. Awesome. In this scenario, I have a job which needs a 4x4x4. Then I need to have a node pool exact topology. to schedule that workload. Either you pre-schedule it or you use node auto-provisioning. Same thing, another node pool, larger slice, you're going to create exact node pool for it, et cetera. All of this is basically you're creating an infrastructure provisioning at the time of workload scheduling that's so tied to your node pool. It's going to make it a rigid node pool creation or rigid management of your TPU. That is basically going to make you slow your job startup time. And we see all the way from 5 to 15 minutes, many times more than 20 minutes for a larger slice. And let's consider a scenario. This is where a quiz comes to you guys now. So I have two node pools on your right, and the first node pool at the top has a workload running on it. And the second node pool is about 64 TPU node pool. It has all the jobs have been completed on it. It's available. Now on the left, I'll want to schedule a job of 4 TPU VM. What happens? Does this job get scheduled on the second node pool, which has 64 TPU VMs available, or a new node pool will be created for this? I thought this is going to be like everybody's going to shout it out, the answer. OK, now let's do 1, 2, 3. Go for it. New. Good job. Awesome. Amazing. You're right. Because we have this rigid configuration and infrastructure creation that was with the slice creation. And GKE also provides you greater resiliency. When something fails, we are going to make sure we recover it for you. And in the recovery process, let's consider I have a larger node pool. This is about 128 nodes, running all great, amazing. All of this are going good. What happens when something fails? Let's say consider there's one single failure, VM fails in this node pool. We have to recreate an entire node pool with the 128 healthy nodes. This is like tearing down your node pool and re-provisioning your entire infrastructure again. Great, it provides you resiliency, right? It keeps your job running. However, this can be a slow process because it is tied up to your infrastructure creation. And comes the dynamic slicing. Dynamic slicing on GKE is a complete paradigm shift. You pick anything I say in the session or not, I want you to pick this one. By decoupling physical infrastructure creation from workload scheduling, we have removed the overhead and headache of the rigid infrastructure management. Instead of waiting for a specific node pool configuration to be created per your workload and managed, GKE intelligently forms the slice for you that you need for your workload at the time of creation. And this provides us a dramatic reduction in the job startup time and accelerates the recovery. We'll talk about all of this and see how it is. Before I go, I want to talk about the layers that actually enable us to do a lot of these functionalities. Dynamic slicing is, we have exposed dynamic slicing on TPU all-capacity mode. Has anyone know? This is a new capacity mode that was introduced with Ironwood. And anybody know about this? Hands up? Awesome. Not Nova from Anthropic. OK. So TPU all-capacity mode is basically your raw horsepower. It's a raw dense reservation. And one thing to remember is that you can improve the performance by co-locating your workload. That's possible with TPU all-capacity mode. And on top of this comes cluster director capabilities, which provides topology awareness and health. Wait a minute, I'm talking a lot of gibberish, right? Sometimes topology awareness and health. It actually means that you can now see your capacity, all the capacity you've received, and the health of the capacity. Not only the VM's capacity, but the TPU fabric health. Overall, complete end-to-end health vision is provided at the cluster director foundational capabilities, along with many things else. And this is then pinnacle to dynamic slicing, which uses all this technology and provides you the next level of workload recovery, accelerated job startup, and improved fleet utilization. Let's go see how. Before that, there's a prerequisite. Here, I just want you to pay attention to this, is that instead of creating a node pool when your workload is scheduled and to exactly what your workload needs, instead, we are going to treat node pools as this basic infrastructure. You're going to take your capacity and pre-configure your node pools as a 16 VM node pool. And why 16 VM? Because in Ironwood, this is called a cube, 4 cross 4 cross 4. And this is the basic building block of Ironwood and the smallest failure domain. And this is a one-time activity. You create, take as much of your capacity, and then convert it into node pool, and that's it. One time, let's get it done. Now let's see how we are going to schedule workloads on it. Now there's a workload that comes, and there's a job that needs 8 chips and 2 VMs. I do have a node pool that's already been created, and for the very first time, you will be able to schedule this workload through dynamic slicing onto the existing node pool, which only needs 2 VMs within it. Otherwise, you had to create the entire node pool exactly that. Another one comes, and then we bin pack it. We make sure that we bin pack so that way we are not using different node pools for different parts of it, and we utilize your TPU to the maximum capacity. And then the third comes, there you go. So this is also sometimes we refer to as sub-slicing. And this is the first time you're able to create multiple workloads within your node pool. One interesting thing here is also that when we are scheduling, we make sure at the runtime we fabricate, we connect your VMs with the TPU ICI links, and then schedule your workload. This helps us to make sure the runtime, the health, and checks, and make sure that this is ready for you before we get your workloads on. And the other paradigm shift that we are bringing in dynamic slicing, that's called incremental node pools. What happens, this is a question back to you guys, what happens when you create a node pool in GKE for TPU, and let's say you are asking for a 16 VM node pool, and there's no capacity for all the 16 VM to be healthy. What happens? Does it fail, or does it provision? OK, again, I repeat. You're going to go create a node pool, say, hey, GKE compute instance create node pool. I want 16 VM of TPU. And then, unfortunately, we don't have in your capacity, we don't have that. And there's only 15 VMs available out of 16. And what's going to happen? Basically, your node pool fails. TPU is all or nothing. We have to make sure that the slice is formed in advance, and it's an all or nothing. If we can find all the healthy VMs, then we schedule your node pool. Otherwise, we do not. And for the very first time, we are providing your partially healthy node pools. And then when an unhealthy node within that node pool becomes healthy, that's when it automatically gets added into the node pool. Now, can you tell me what's the advantage of this? Why would you need this? Why would you need this? Sorry, what? Exactly. These are expensive resources, and you want to use whatever you have, and then that's what it is. So I have listed all the advantages here, right? One is 100% access to your TPU healthy capacity. You can utilize them now with sub-slicing, where you can use smaller 1 VM to schedule your workload within a node pool. This helps you, right? You can optimize your workload utilization. And second is, if you use TPU, if you use accelerator, if you use AI, you do know you have to constantly keep creating this infrastructure until you get it. Many times there's a failure, and you have to keep going at it. OK, let's create, sorry, it failed, or let's create, it failed. Now you don't have to worry about it. Just create it. Whenever things get healthier, we'll add it into your node pool. So you do not have to worry about the operation toil that's involved in this. And maximize your TPU utilization. Now I'm going to switch to forming larger slices with dynamic slicing. We saw the smaller slices being bin packed into a node pool. Now what happens when I want the slice to be greater than 16 VMs? In this case, I have a job that needs about 128 TPU VMs, 512 chips. In this case, GKE, or the dynamic slicing scheduler, is going to pick 8 healthy node pools, 8 because 8 node pools catch up to 128 nodes. And once it figures this out, it's going to work with the TPU infrastructure underneath to form the network TPU fabric. That is your fabric. That is what we call it as a slice, getting them together and get them into a single ICI domain. And this is what happens. And I've shown you in the 3D dimension here just because this is ironwood, and that's how it works. And those tiny, tiny, small, very bad arrows that you see on each one of the node pool is a wraparound link. And this is how it looks. So, and this was formed all dynamically at runtime for you within few seconds compared to the minutes that it would have taken if you had to create the node pool for it. And this is a simplified version. Do you want to see the full version of how internally it happens? Like, what does it look like? I'll just quickly show it to you. There you go. This is actually what happened. So on the right, you can see that, and if you see the red squares, those are the VMs, and they're all connected with X and Y and Z dimensions of ICI connections and the wraparound links. All of this was done by our magical TPU OCS switch logical operator that brings them all together and builds the network fabric, and GKE works with that at runtime to form the slice to at the fastest pace that we can do for you. Let me get started. So if you want to use this, how are you going to use this? Quickly, create your node pools, and then you also have to install a slice scheduler at one time if you want GKE to let you schedule all of this. And that's it, submit a workload. When you submit a workload, important thing to note, add this annotation, please, so that we know that you want us to do dynamic slicing. It also does two work, know that dynamic slicing. Two, what topology that you need, right? And then apply a workload, and we will create the slice and schedule it for you. However, under the hood, let me tell you what happens under the hood. So when you submit a workload with this annotation, what the scheduler does it, as I said, it's going to pick a healthy node pools that matches the VM for the topology. In this case, 8 node pool, and create something called slice CR. We have a slice controller that's been deployed onto the cluster. You have to enable it, and then the scheduler creates a slice CR and gives the ID of these node pools. It's called partition ID. It's the node pool ID is kind of maps to node pool ID. And if you know ironwood, it's nothing but a cube ID. And you provide that, and then submit the slice CR, and the slice is created, and scheduler schedules on it. Let's see this live in action with a demo. Let's go for it. And you might have to forgive me for big fonts here, but awesome. I have a workload here. It has the annotations. Let's get into it. And here's the annotation, and I've picked a large slice. That's about 2048 TPU chip. Let's see how it fares. I've just purposely picked this slice. Let's see how it fares. And this is all the annotation that you have to put. And then the rest of the annotations are very typical TPU annotations, like I want to pick ironwood and things like that. So after you do this, let's get out of this and then go ahead and deploy the job set. So I've deployed the job. Now let's look at the job set. And definitely it's suspended because there's no infrastructure, right? And because the infrastructure needs to be created, let me watch for the job, what happens on the left, and we'll see when it starts running. And on the right-hand side, while this is happening, we are going to go describe and watch the slice. Because as I said, we are going to create a slice here underneath, and you can see it. And it's activating. It's already created the slice CR, and it is activating the slice. It provides you the live status so that you know what is happening. And let's wait for it. Hopefully it comes. Yes, there you go. And it's now active. And the slice has been formed, and you can see on the left that your job has been running. So that is all it took, and there was no editing in this. That was all end-to-end. And you can also see it provides you the age. So it only took about 41 seconds to form a 2,000 TPU chip slice. This is actually, if you have used any accelerator, forget about TPU, you know what's the value of it. And now let's look inside the slice, right? Like how many node pools it picked, what was the partition ID, et cetera. You can go describe it, and as 2048 is 128 node pool, GKE selected these node pools, scheduled and created the TPU fabric, working with underlying layers, all of this created within just 41 seconds. which could have otherwise have taken you 20 minutes, about 15 to 20 minutes. And you can also see the status of it. And now, let's take a look and scenario what happens when the job completes the execution. So let's watch for the slice, and let's wait for the job to complete on the left. And it's going, yes, yeah, awesome, it's completed. On the right, you can see that we are deforming the slice. So we do not want to keep the slice running because we want to make sure the infrastructure is given back so that it can be, we can schedule other topologies and slices after that. So the next few slides, I'm going to talk about the recovery and how does the recovery work in dynamic slicing. Here I have the 8x8x8 that we created earlier. And let's say one of the VM within one of the node pole has failed. And in this case, what we do is we are just going to deform the slice first to make sure that there's no use of the slice because job cannot run on it. And we deform the slice, and we are going to pick another healthy node pole, and we are going to swap it, hot swap it, the other node pole, and then we do the magic again of restitching the fabric together with all of them, and the slice is formed. And this also comes with it actually gives about 5 times improvement in recovery compared to our static node pole. Overall, before I go and I get Artur on the stage, I just want to say that what you get out of this is maximizing your performance. Time and resource is extremely valuable for the costliest chip that you have purchased out there, and we want to maximize that performance for you. First, faster job startup. Second is recover faster. Third is maximize your TPU utilization and get that flexibility. And we have worked relentlessly and thankfully with Anthropic to co-design many of these features. They've gotten access to these when things were really buggy, and they've worked with us, and then we have given us great feedback. And now Artur is going to tell his journey and then how this has helped them. And then he has some cool slides that's going to tell how many seconds, minutes that he has saved with all of this. Let's bring Artur on back here. And Artur partied a lot last night, so his voice is a little down, OK? So excuse him for that.
Thank you, Kavitha. Good evening, everyone. Hopefully, I won't stand here too much between dinner and this. But yeah, it's a pleasure to be here. My name is Artur. I'm a member of technical staff at Anthropic within the infrastructure team. And as Kavitha said, we've been co-developing some of these features for the past 2 to 3 years in TPUs, and we're kind of really fortunate to be witnessing they come as like first-party features for the rest of the community. And as Kavitha said, I want to kind of walk over what these at least past 2 years have looked like. To set the stage, one thing that might be different from other companies is that Anthropic operates with a fairly static capacity, at least at a given time. So we don't have auto-scaling for a particular use case at our scale or in a frontier scale for the TPUs themselves. So going to 2024, that's when we got kind of our first kind of V5 fleet. And these are primarily non-elastic, as I just said, capacity. And it meant that failures lead to node pools deletions, as Kavitha was saying. But that was also when we kind of get started with sub-slicing. We internally call it kind of hard slicing, and Kavitha has done a good job like outlining what that looks like. But basically, you have to create a node pool specifying the specific topology that you want. For V5V, that might have looked like a 16 by 16, and for V5P, that would have looked like as a 4 by 4 by 4. If our requirements change for that specific topology, maybe because your training run is complete and now you want to serve inference, you need to delete all of those node pools and recreate them again as smaller topologies. And that might take, in the best case scenario, 10 to 15 minutes, but in some cases, it might take even longer. And you're also capped at the amount of those operations that you can do in any given cluster. For that reason, plus because sometimes nodes go bad and they fail, we've all experienced this, we've developed a process that's called Maximizer internally. Basically, its intent is to kind of get access to as much capacity as we have acquired from Google in an optimal and automated fashion. So here we can see a snapshot in time. We have a 16 by 16 that's fully healthy. Again, this is back in 2024, so we don't yet have the functionality that Kavitha just outlined. We have an 8x8 that has gone unhealthy. Then we have a few other smaller topologies spread around kind of our capacity. And I've included here one specific host that's in repair. Basically, this process is going through a few specific steps. First, it's going to delete the unhealthy node pools that we might have. That's a process that we have to take first. Then it's going to try to transform those smaller topologies into bigger topologies, because those are, for most cases, higher value to us than the smaller ones. And this back then happened through a process called priority boost, where basically Google automatically preempts the smaller topologies into bigger ones if we want to. At some point, for example, in the bottom one, or the bottom right one and the top right one, we wouldn't be able to have created those 16x16s because, again, we have hosts that might have failed there. And in that point, we would get a stock out, and this process then repeats for the smaller topologies, going to 8x16s, 8x8s, 4x8s, 4x4s, all the way to 2x2s if needed. So we're running these processes on a frequent basis just to ensure that we have high availability of the slices that we have paid for. But then at the end of 2024, we also get access, very early access to this sub-slicing feature that Kavitha just outlined, but this time within a static node pool and with no dynamic slicing. This was all happening at runtime. Basically, we would acquire a 16x16, again, through a static node pool that we just provisioned. But then at runtime, thanks to tight integration with our own scheduler, we would carve out that 16x16 into smaller topologies at runtime, depending on the internal requirements that we had. This was already a first glimpse into kind of these new really time savings that we can have with GKE dynamic slicing. As opposed to having to delete the node pools, again, 10 to 20 minutes, and recreate them as smaller topologies, we will be able to do that within seconds at runtime, thanks to this deep partnership with Google. Then 2025 came, and this was when V6E got onboarded in Anthropic, and we again had this access to some new features that were really interesting. The first one was restarting place. Basically, we just kind of covered a case where one of the hosts went bad. So let's say that we have a 16x16, we were using it, everything was fine, but then a host goes bad and we send it to repair, which is a process that Google takes care internally. And at that point, before, we would have to delete that node pool through the maximizer process and recreate the smaller sub-slices around it. But now, thanks to restarting place, we could keep that node pool intact. So we wouldn't have to go through node pool operations, which are somewhat slow. And instead, we can now sub-slice, to combine the feature that we just described, sub-slicing, with restarting place to kind of use that node pool to its max availability. Once that host was ready again, we can reuse it as a 16x16 as intended with a static node pool. The other feature that we got back then was the ability to have stable hardware identifiers. Each time that you provision a node pool and reprovision it, you would lose kind of these important identifiers, specifically the host tray ID or the TPU tray ID. And for a company our size, it was actually a big deal. We have very specific processes whereby we want to kind of test that the hardware is stable and that we kind of have run burn-in, and we have different levels of confidence and different kind of workloads that we might run on them. So having the ability to track an asset throughout its lifetime as node pool operations happen was quite useful. In this particular case, we can assume that the TPU chip itself has failed, but the host tray was fine. And in that case, the host ID would have been kept, and the TPU chip would have changed. The other thing that we got towards the end of 2025 was a first party of availability of the host coordinates. This is a core feature for us to do the sub-slicing. To perform that runtime sub-slicing, we need to tell JAX exactly where the workloads, we need to know exactly where to kind of land the workloads itself on the physical hardware, but also be able to tell JAX where those things are for each one of the processes, the JAX processes. Before, we were doing that through our own custom process that would take roughly 10 minutes. Once we ingested the slice, we would have to run a specific JAX program to map everything out. But now, towards the end of 2025, we got that as a first party label within the nodes themselves in GKE, completely eliminating this 10-minute process and having that information like firsthand, knowing exactly where each one of the hosts was for the purposes of doing sub-slicing. And finally, one thing that's quite interesting for me, at least as an infrastructure engineer, is the ability to kind of visualize what the Google data center looks like internally at Anthropic, which was pretty nice. If we only had node pools and we have those small node pools, we would kind of have these 2x2s or 2x4s floating around, and we wouldn't necessarily know exactly where they were internally. But again, thanks to these new kind of identifiers, we could exactly map each one of the racks in the data center from the Google side, We would know which hardware we have gotten before and which have re-entered our infrastructure. And we would also even know exactly where are the specific hosts that we haven't been able to acquire yet at that point, on this picture highlighted in white at the bottom right. These moves us all the way to 2026 with a V7X capacity that brought kind of the features that Kavitha just highlighted. And at this moment, I'd like to highlight how we specifically use them, thanks again to some of the flexibility that Google continue to offer us at Anthropic. The first one, which Kavitha covered, is incremental provisioning. This was huge for us because we have this maximizer process that's running across our whole capacity on a frequent basis. But now we're able, as soon as we get like new capacity, as we just did with V7X, to immediately provision it, even if we have hosts that are not immediately available because they have failed hardware. In this specific example, we have a 4x4 cube that has 3 hosts in repair. In this specific moment, we can create it, and it will come as a node pool. We can see all of the hosts, but we know that 3 of them are in repair, so we might not be able to utilize it fully. And this is a new functionality that we have with Cluster Director. Once those hosts are back to healthy, we can then make use of that 4x4x4 to its full extent. And speaking of Cluster Director and the ability to use those node pools, this moves into dynamic slicing, and in particular super slicing, which we're really excited about. And at Anthropic, we have our own scheduler. I think Kavitha just highlighted how folks can use it through Q. At Anthropic, for the past few years, we've been kind of developing our own scheduler because we had very early requirements around topology awareness. We have kind of very tight latency thresholds, and we kind of bind pods directly without going through the default kube scheduler. So we have our own custom scheduler. But the nice thing is that these features, we can pick specifically which ones we want, then Google gives us access to the underlying custom resources as slices, as Kavitha just highlighted. So in this case, let's say that we have provisioned 2 cubes and they're fully healthy, 2 4x4x4s. And they're provisioning this specific mode called provision only, where the ICI links are not yet activated. A new job comes in. A job is a workload internally, how we call a workload internally at Anthropic, and it requires 2 cubes in this case, so 4x4x8, 32 pods that stay pending. Our scheduler, which performs gang scheduling, and it's aware of the topology, it knows how to kind of preempt and not preempt, and how to score different jobs between themselves. But for now, let's just assume that we have kind of free capacity to make things simple. It's going to identify that these 2 cubes are available, and it's going to bind those pods before the slice is created. We introduced a new component called Slice Manager that will then see that we have all of these pods bound, but not yet available to run because they don't have that ICI domain yet. So it then creates that slice CR directly. So the same thing that Q was doing in Kavitha's slides, we do ourselves directly. And we specify the partition IDs. And we have those IDs as first-hand labels on the nodes, but also to Cluster Director if we need to use them. This slice is still not ready, and it's going to be activating. Once the slice is active, and that's, again, happening because we have direct access now through slice controller that's enabled in our clusters, all the way through the OCS hardware in the Google data centers, it's going to go activating. And eventually, it will become ready. And we can visualize that, as Kavitha just showed in her demo, through the slice CR specifically. Once that is done, our program can start, and we can initialize JAX. Once the workload is completed, it's simply a matter of deleting the job, and the slice is going to get orphaned. And we ourselves, because we're doing everything ourselves, can delete the slice, and the cubes are back to being available for new workloads to run on. The other thing that we have now with Cluster Director and the slice CRs is the ability to go an even deeper level with sub-slicing, even in previous topologies, such as V6Z, there are 2D. So without the slice CR, with our previous way of doing kind of sub-slicing, if we have kind of, for example, 2 links fail in a 16x16, we wouldn't necessarily know exactly what have failed there. Is it a link or is it a host? We wouldn't know. So we have to take the worst case scenario. We have to assume that these 4 hosts in this case, on each side of the links are bad, and we have to use just the other parts of the slice, the 16x16s that are healthy. But now with Cluster Director and the slice CR, we can know exactly that all of the hosts are in fact healthy, and specific links between different topologies within the partition tree are unhealthy. So we can fully still utilize the hosts, not the full ICI bandwidth within that slice, but all of the hosts nonetheless. And that's a huge win at scale. Finally, I want to show how the hot swap functionality that Kavitha just highlighted works internally, even with our constant scheduler. Let's say that we have a 4-cube job here, highlighted that we've created ourselves. One of those hosts within these cubes go bad. Now it's a matter of simply deleting that slice, creating a new slice where we've swapped that old cube for a new cube. That again is done through Slice Manager, this new component that we introduced, and creating the slice that's going to be activated, and everything's fine again. And we can go all the way of keeping all of these other pods in the other cubes in place and just waiting for this new, newly created cube and newly joined 16 pods to join and reinitialize and restore from a checkpoint and continue. A paradigm shift from the previous behavior on V5P, for example, where you had to kind of tear down the whole thing. So to summarize, this is one way of looking how one would use what the ICI domain for V7X is, so up to 9200 chips have changed over the years. So with V5P, we would actually need 2 pods connected over DCN to get to that scale. With V5E and V6E, which have a different, optimized for different use cases, you would actually have to connect 36 16 by 16s over DCN. And now with V7X dynamic, especially with dynamic slicing, you have 144 cubes in the same ICI domain. Your replacement unit back in V5P would have been the whole kind of pod, so half of that, half of those chips. In the V5E, V6E kind of model, you're replacing 116 by 16. And in the V7X, you only replace 16 of those nodes, or 64 chips. And finally, what this means to us at the end of the day. Well, my job's at least a little bit easier, and it's directly translating from hours into seconds. If you think about host provisioning, we would have to go through this maximizer process that's kind of attempting to get all of the capacity. We don't know exactly if hosts are bad or not, so we have to keep attempting and going to smaller and smaller topologies. Now with incremental provisioning and cluster director, we can immediately acquire that capacity once it lands, knowing that when hosts kind of go back to healthy, they're going to join the node, they're going to be marked as healthy in the node pools, and we can fully utilize them. For slices themselves, because we had to do those node pool operations, it would take from 10 to 30 minutes. And now it only takes 20 to 60 seconds with GKE Dynamic slicing. The visibility from an end-to-end perspective was really opaque, and now we can know exactly what has failed, links, hosts, or both. And the recovery from failures is also much faster. Before, you'd kind of even take hours to kind of recover from those failures, depending on exactly what had failed and the many attempts that you'd have to do. And with GKE Dynamic slicing, this translates to 2 to 5 minutes because you can do that hot swapping. Sub-slicing, very specific to Anthropic, we've co-developed and unavailable on V5P. Now it's a first-party kind of feature that we can use directly through the slice CCRs. And the fleet visibility to actually see all of the capacity that we have acquired, it would have taken weeks back then. And now we can instantly see it and build that kind of nice TPU hardware map instantly through Cluster Director. That's it. Thank you so much. Hopefully this was a nice glimpse into how we've co-developed.